All right, guys, we are starting a new unit today. This is actually chapter 9. So we went from chapter 3 to chapter 9. We will come back and hit the other ones, but this is something that we're going to cover before we do congruent triangles, and we'll see what the relation is between the two things shortly. Okay, so today we're going to talk about transformations, specifically a translation. So on the agenda for today, we're going to go over the Chapter 9 targets to kind of give you a preview of what's to come and see what you think or what you already know about those types of things. We'll do notes on translations briefly for a few minutes. So you will need a notebook out or something to write down here. We'll do practice problems over those types of things to make sure you've retained that information and can apply it. And then you should have time in class to start the homework, potentially even finish it. So you have a handout that lists the targets for chapter 9. There are 4 of them, A, B, C, and D. What I want you to do right now is go down the list, read each of those targets and the sample problems for those targets, and then decide how you feel with those. So 1 being like you have no idea what it's saying and you have no idea how to start the problem. 2 being I have an idea what to do, but I'm not sure if it's the right thing, but I can make some progress on it. And then 3, you feel like you've mastered it. You feel like you know exactly what it's asking and you know how to do it. So on the right-hand side, you can fill in today's date in the first column and assign yourself rating for each of those sections there. You can do it for the target and the problem in the target as well for those specific problems if you want to get a little more specific. So go ahead and pause the video to do that and then hit play when you're ready to resume. Okay, at this point you should have out your notebook to take some brief notes here on some new ideas and some new vocab that we'll use a lot. So a transformation is basically something you can do to a figure or a shape to arrive at a new figure or shape. And it can involve movement of certain types. 3 of those that we'll talk about in this chapter are translations, reflections, or rotations. And today is going to focus mainly on translations. So the pre-image is a name that we call the figure before anything's done. So think of that as pre-transformation, before anything's happened. And the image is the name of the figure that's the result of the transformation. So pre-image, original, image, new. Okay, so to see a couple examples of this, we have 3 transformations here. They're the 3 listed above. We're going to try to identify which is which though. So in number 1, we have this turtle being flipped over this line. So this is a reflection. So the top is the pre-image and the bottom is the image. I guess depending on how you're looking at that, you could certainly make an argument the other way because there's nothing to indicate that here. But we're going to get some notation shortly that will tell us which is definitely where we started and where we ended. So number 1 is a reflection across the line. Number 2 is just a translation. So maybe if we started at the top, this is just shifted downward some amount. And number 3 is a rotation. A rotation happens about a point. So maybe there's a point right here between them that if we held down that turtle and rotated it 180 degrees around that point, it would end where we started. Or I'm sorry, it would end on the bottom if we started on the top. If we started on the bottom, we would end at the top. So it's all depending on the perspective here. But either way, it's a rotation, 180 degrees to be precise there. Okay, so all of those are called isometries, which is a really important word here. Make sure you get that down. An isometry is a transformation that does not change the size or shape. So from pre-image to image, we have the exact same thing, the exact same size and shape. Some places it's called a rigid transformation or a congruence transformation, but in all of those examples, same size, same shape. Okay, of the 3 down here, 1 of them is not an isometry. The other 2 are. I'll give you a second to think about that. So which one of those, if we map the pre-image to the image, and again, it really doesn't matter which way you look at it here, which one of those does not preserve the size and shape? Okay, so it turns out that number 4 is not an isometry. So the size has changed from one figure to the other. So the size has not been preserved. The shape has been, and we will talk about that. That's a different type of transformation, but it's not an isometry. 5 and 6 are both isometries. It looks like 5 we had a rotation, and 6 we had maybe a reflection and then a translation, but the size and shape are both preserved in both of those examples. So the main thing we're going to focus on today is a translation. So you can think of a translation as just like a slide. Like if you were to put your hand on your desk and move it just left, right, up, down, any combination of those without turning it at all, you'd be translating your hand. So the picture here is an example of that. We have the polygon NCHS, and that's translated over to the polygon N prime, C prime, H prime, S prime. You can just say NCHS prime if that's easier. But that little tick mark above each letter we pronounce as prime, and that is to indicate that that is the image. So where the prime marks are is where the transformation ends. Question is a translation an isometry? And yes, clearly if I translate an image, it's not changing the size or shape of it. Actually, all 3 of the things that we've looked at so far are isometries. They're not changing the size or shape whatsoever. Okay, so now we're going to look at 2 different ways that you can record translations, or 2 different notations for keeping track of them, you could say. So I'm going to look at an example. First, we have a triangle KAT, and that is the pre-image. The image is K prime, A prime, T prime. Triangle K prime, A prime, T prime. So we're going to try to see how far did it translate. So what I do is I pick one point out, let's say K, and I'm going to look at what did it take to get from K to K prime. Well, I went to the right 8, and then I went up 4. Now I picked K arbitrarily. You could have picked a different one, and you would have got the same thing because the shape and size stay the same. So let's see, from T to T prime, it is to the right 8 again and up 4. I'd encourage you to try that with A to A prime would be the same thing. So one way that we can describe this is by saying that all of the points, all of the ordered pairs x, y, get mapped to new ordered pairs where we take the original x and add 8 to it, and take the original y and add 4 to it. So this is called the coordinate notation. You have an original set of coordinates x, y, and the new set of coordinates are given by this rule. And if you check that, if you take K, it has coordinates of -8, 5. And if you check where K prime is, that's 0, 9. That clearly follows this rule. If you try to add 8 to the x and add 4 to the y, it would get you to the image there. The other notation we can use is a vector. So this is a new concept. A vector looks very much like an array, except the difference is array continues indefinitely. It goes on forever, whereas a vector has a finite length. And the length of a vector, we just call its magnitude. So to distinguish between where we start and where we end, we put an arrow on the terminal point, the spot where it ends. So this J here is the initial point and M is the terminal point. So the way that we write this, vector Jm, it looks almost like a ray. This should be with one arrow coming off of it like that. The component form of this is just describing how far right do we go, and then how far up or down do we go. So we go to the right 5, and we go up 2. So the component form of this vector, we write those almost like a coordinate, but we put these angled brackets around it to show that we're talking about the direction of a vector. So if you know that direction, you also know the length as well. I'd encourage you to think about that. You could use Pythagorean theorem to find the length because this is a right triangle. Not totally important for today, but that is how you would find the magnitude of a vector. And if we take a look back at the other example, you could describe this as a vector too. If I look at from T to T prime, there's a vector that takes me from T to T prime, and it has those components of 8 and 4. So the vector 8, 4 describes the transformation that happens here too. You can hopefully see that that and this are very similar. They're just different ways of writing the same thing. So what we're going to do now is take those three practice problems and have you try them. So I'd encourage you to pause the video right now. Those 5 practice problems. You have 5 on the front and 1 on the back. So 5 on the front, 1 on the back. You have 6 practice problems to do. What I want you to do is pause the video and try to do them right now, and then resume, and I will go over the answers. Okay, so number 1, it says the point A, which is 3, 2, gets transformed using this translation. What is the image? So A prime would be 9, negative 1. If you add 6 to the x value and subtract 3 from the y value. Same thing on 2. B prime would be 2 and negative 2. Okay, 3 and 4 are a little different. It's saying what's the pre-image if you know the image. So we're looking for C. So not C prime, they've given me C prime. So we have to ask ourselves, kind of thinking backwards here, what number had 6 added to it to get to 2? And that turns out to be negative 4. What number gets 3 subtracted from it and gets us negative 7? That's also negative 4. That's a coincidence here that those are the same. But if you try to put those through the transformation, by adding 6 to negative 4, you get 2. By subtracting 3 from negative 4, you get negative 7. So similarly on 4, this one would be, what do I add 6 to get negative 3? That's negative 9. And then what do I subtract 3 from to get negative 2? That is 1. Okay, number 5, the coordinate notation, if we start at 5, negative 2 and end at 2, 0, the coordinate notation says we take x, y, and map it to, well, if I started at 5 and ended at 2, that means it was x minus 3, subtracted 3. And then if I started at negative 2 for the y and ended at 0, that means y had 2 added to it. Okay, the component form would just be the vector negative 3, 2. So the point travels along that vector, basically, to get to the image. Okay, and then number 6, if I plot this triangle, ABC, A would be right here, B would be at 4, negative 1, so right there, and C would be at 2, 4, so right there. So I have this triangle ABC, and what I want to do is put the whole thing through this translation. Now all I really need to do is do those vertices, A, B, and C. If I put A through the transformation, so if I subtract 3 from the x and add 5 to the y, I'm going to get right here. So this is A prime. If I do the same thing with B, if I subtract 3 from the x and add 5, I'm going to get right here. So that's B prime. And then with C, if I subtract 3 from the x and add 5 to the y, I get right here. So the idea is triangle ABC gets mapped to this A prime, B prime, C prime, but the size and the shape stay the same. So this is definitely an isometry. All right, what you're going to work on now is the homework for the rest of the time. You have this little half sheet with 3 graphs that you're going to use for the homework, just for the problems that it says to graph for. If you don't have that, ask the sub for that to make sure that you're doing graphs on this sheet. Here is the homework. It's on Google Drive, but if you'd rather pause the video as I scroll through these to have the problems right here, you can do that. So I will scroll through it slowly and you can pause to see the particular problems you need to work on. So tomorrow we'll go over this in a little more detail to make sure it's solidified with you and you got everything you were supposed to. But until then, try your best on the homework. If you have questions, I will answer them in class tomorrow.